And now we can look into the next topic, which would be gravitation. Gravitation, and it says that we have our planet Earth and we have an object here. Excuse me. Look at the Earth right now. We have two objects, let's say M1 and M2, and there's a distance r between them. So the force of gravitation would be proportional to the product of masses and inversely proportional to the square of distances combined. It would be proportional to m1 m2 by r square. So we put the constant of proportionality to make it into an equation. So g m1 m2 by r square is equal to f. Okay, where g is the constant of proportionality, just the gravitational constant as well, basically. Okay, and if one object is, let's say, a very huge object, for example Earth, and the other object is very small as compared to Earth, so capital M and small m denote the distance, and we have the uh, distance between the centers as r. So the equation gets the form gmm by r square. Yes, where this is re and this is h, so r is equal to re plus h as well. Okay, radius of Earth plus the height. So there's one more thing, which says that force exerted is equal to the weight, which is mg. So this is one form and this is the other form, and they're approximately the same. So mg is equal to gmm by r square. So m cancels out. What we get is g is equal to gm by r square. So this is the acceleration due to gravity in terms of gravitational constant, mass, and the radius of Earth, plus of course the height the object has above the surface of the Earth, if any. So in other words, g could also be equal to gm by re plus h whole square, depending upon the situation. H can be considerable value and h can also be 0 if the object is right on the surface of the Earth. Okay, centripetal force, interesting topic. in case of centripetal force, we have to keep this circle and triangle in mind. The circle says the linear velocity is tangential and the radius is r, and the centripetal force is directed toward the center of the circle of rotation. And there's one more thing, we need to take out the segment, the arc, in terms of this here, the differential circumference delta s, and the radius and the angle theta. Okay, so we need to estimate the centripetal acceleration, yes, which is the ratio of differential velocity to the velocity by differential arc to the radius, which is approximately the same, and which suggests that delta S is equal to r delta v by v. And delta S is also equal to delta S by delta t is equal to v differential displacement by differential time is equal to differential velocity, or just instantaneous velocity in this case. So it says that delta S is equal to v delta t, so this is the second form. Now we equate 1 and 2, so r delta v by v is equal to v delta t. Okay, so delta v is equal to v square delta t by r square. Okay, just one moment. Just delta v by delta t, which is rate of change of velocity with respect to time, is equal to v square by r square. In this case it is a ac a sub c, which is the centripetal acceleration, which is v square by r, excuse me, not r square but v square by r. V square by r. So now as we know that F is equal to ma, so Fc is equal to mac, the centripetal force is equal to m into centripetal acceleration, which suggests that Fc is equal to mv square by r. So this is the form we are looking for, the centripetal force. It's very important. But there's one more thing to it. As we know that v is equal to r omega, the linear velocity in terms of radius and angular velocity. So this suggests that f is equal to m r omega whole square by r, which means f is equal to mr square omega square by r. So f is equal to mr omega square. So this becomes the form in terms of the angular velocity for centripetal force. See, and now angular momentum. Angular momentum. Yes, as we know that linear momentum P is equal to mass into velocity, and the angular momentum is equal to r cross p. Okay, so we make the substitutions. L is equal to r cross mv. Okay, and we go further with this, which says that L is equal to m r cross v. Yes, so once again, referring back to the circle situation, here's the tangential linear velocity, here's the radius. Okay, and radius is directly proportional, radius is perpendicular to velocity, so the angle here is 90 degrees. Yes, okay, so so we open it up in terms of the vector product mrv sine 90 degrees, which will give us L is equal to mrv, and sine 90 is 1. Now v is equal to r omega, linear and angular velocity correlated with the radius. So L becomes angular momentum m r omega. L becomes mr square omega. This is an interesting form here. Well, yes, hey, but there's a little bit more to it, as I is equal to mr square, which is the moment of inertia, the product of mass and the square of radius. So the angular momentum could very well be I omega, the moment of inertia into the angular velocity. So this is equation modified. interesting. The work energy theorem. It is significant and it has a mathematical form, and it uses the third equation of motion, which is 2s